Section 4.4 starts taking a look at how we can solve equations with logarithms. Yesterday we took a look at how we solved exponential equations by using logarithms. Today we're going to have logarithm equations that we're going to have to solve by using exponents. But before we get too far into this, we first should address the little issue about domain and logarithms. If log base a of x equals b, then we have a restriction on the domain that x has to be greater than or equal to 0. Actually, no, I'm going to change that. It just has to be greater than 0. It can't be 0 at all. In other words, we cannot have a negative number inside of a logarithm. And that's something we're going to have to check with every one of these log answers, is does it make it so that we have a negative inside the log? In fact, let's write that down. This means we must check our solutions. So with that in mind, let's take a look at solving logs. Two major strategies in solving logs. The first major strategy we use is we write the problem as a single log, and then convert the log to an exponent. For example, if we have log base 6 of x plus log base 6 of x plus 1 equals 1, and we want to know what x equals. Well, we know that two logs added together means we really multiply inside the logs. So we can combine this to log base 6 of x times x plus 1 equals 1. We've now written it as a single log, so we can convert it to an exponent where the base of 6 to the first power equals the x times x plus 1. Well, 6 to the first is just 6, and so now we have something that's going to be really easy to solve. We distribute first to get x squared plus x. We'll subtract 6 from both sides to get 0 equals x squared plus x minus 6. We know now we have to factor, so we have x plus 3 and x minus 2. And then when we set each equal to 0, we get our solutions are x equals negative 3 and positive 2. The only thing we have to be careful of when we have a solution is go back to the x and the x plus 1. Both of these have to be positive. Notice if we plug the negative 3 in, we would be taking the log of a negative number, and that just doesn't work. If we plug the 2 in, the log of 2 is, well, that 2 is a positive. The x plus 1, 2 plus 1 is 3, also positive. So the 2 works, the 3 does not. So 2 is our only solution. With logs, sometimes we'll have one solution, sometimes we'll have two solutions, sometimes we'll even have none solutions. So make sure you're always checking your solutions. We cannot take the log of a negative number. Be careful there. That does not mean if the solution is negative, we have to delete it. That's not the case at all. We don't throw out the negative 3 because it's negative. We threw out the negative 3 because when we plugged it back in, it gave us a negative inside of a log. And we're going to see a few problems on the assignment and today where the negative is good and the positive is bad. Plug it back in. Does it make us take the log of a negative number? That's what's not allowed. How about this? Let's do log base 3 of 2x minus 4 minus log base 3 of x plus 3. And we're going to make that equal to 2. Again, we're going to make this into a single log so we can convert it to an exponent. With subtraction, we know that turns into a single log base 3 that has division in it. The 2x plus 4 in the numerator and the negative log, the negative exponent means the x plus 3 is in the denominator, is equal to 2. Now that we have a single log, we can convert it to an exponent. 3 squared equals 2x plus 4 over x plus 3. And 3 squared, we know that is 9. And so now we can solve this simple problem by clearing the fraction, multiplying by x plus 3 on both sides. And when we distribute, we have 9x plus 27 equals 2x plus 4. Get the x's on one side by subtracting 2x, everything else on the other side by subtracting 27, and that's going to give us 7x equals 4 minus 27, negative 23. And when we divide both sides by 7, we get x equals negative 23 sevenths. Of course, we always want to check our answer. And if we plug negative 23 sevenths into the first log, multiplying by 2 is going to still be negative, and subtracting 4 is going to make it even more negative. When we plug negative 23 sevenths in, that first log becomes a negative. We have to throw that answer out, and this one actually has no solution. Because that first log ended up negative. The second log would have ended up positive, but the first one ended up negative. It's outside of the domain. So that's the general idea to the first strategy to solving logs. We write as a single log and convert it to an exponent. And with all of our problems, you always want to check your solutions. Our second strategy is if log base A of B equals log base A of C. We've got a log on both sides, then the insides, then B equals C. This is kind of like saying if the bases are both equal, then the exponents are both equal. This is exactly the same process. So if we have log base 3 of x equals log, oops, helps if I copy the right problem. How about, let's try this. Log base 3 of x plus log base 3 of x minus 3 equals log base 3 of 4. Again, addition tells us that we need to write this as a single log that's multiplied together. So log base 3 of x times x minus 3 equals log base 3 of 4. Notice both sides have the same log base. If those bases are the same, then the insides must be equal. And if we distribute, that gives us x squared minus 3x equals 4. Subtracting 4 from both sides gives us x squared minus 3x minus 4 equals 0. And we're well on our way to solving by factoring to x minus 4, x plus 1. And of course then x equals positive 4 and negative 1. Plugging 4 in, the log of 4, that's a positive. 4 minus 3 is 1. The log of 1, that's a positive. 4 is good. But if we plug the negative 1 in, you see it makes both of those negative. And that's going to be no good. So we do have to throw out the negative 1. Because we cannot take the log of a negative number. So our only answer for this one is x equals 4. Let's try one more of these. Let's do the natural log of 2 minus x plus the natural log of 5 minus x equals the natural log of 18. Again, this one has a plus in the middle. That means we're going to multiply them together. And let's just go ahead when we multiply them together. FOIL, 2 times 5 is 10, minus 2x minus 5x plus x squared equals the natural log of 18. In fact, let's simplify in the middle there. 2 minus 5, 2 negative 2 minus 5, that's negative 7x. So that was just all of that distributing is what we did. Now we've got the same base on both sides. Remember, natural log means base e. If they've got the same base, then the inside stuff must be equal. 10 minus 7x plus x squared must equal 18. Making it equal to 0 by subtracting 18 from both sides. We'll also put it in order as we do this. X squared minus 7x minus 8. Factor. X minus 8, x plus 1 equals 0. Set each factor equal to 0, and x equals 8 and negative 1. Of course, we need to check these answers, and notice this time when we plug the 8 in, 2 minus 8 is negative 6. 5 minus 8 is negative 3. Both of those logs have negatives in them. We cannot have a negative inside a log, so the 8 gets thrown out. However, when we plug negative 1 in, 2 minus negative 1 is a positive 3. And 5 minus negative 1 is a positive 6. Negative 1 is a good answer because it doesn't make the logs negative. Notice here in this problem the positive answer was thrown out and the negative answer was saved. We don't necessarily throw out an answer because it's negative. We check the answer and throw it out if it makes the log negative. We don't care about x, it's the log. The log cannot be negative. So those are our two general types of strategies to solve with logarithms. We'll make them a single log and convert to an exponent. Or if we have two equal logs with the same base, we'll make the insides equal to each other. From there we can only really do variations on a theme, and one such variation would be if the problem was quadratic in form. For example, if we've got log base 3 of x, and that is squared, minus 5 log base 3 of x plus 6 equals 0. Notice first that squared is not inside the log, so we can't pull it out front. There's a difference between the log base 3 of x squared, where the squared can move out front, and the log base 3 of x, and the entire thing is squared. We're squaring the log, not the x. So the exponent cannot move out front here. What I do notice is we've got this log base 3 of x, where one of them's squared, one of them's not. This is essentially quadratic in form. So we can factor it where log base 3 of x squared is log base 3 of x times log base 3 of x. And 6 is negative 2 and negative 3, which then gives you that negative 5 in the middle. So now all we have to do is set each factor equal to 0. In the first factor, we add 2 to get log base 3 of x equals 2. In the second factor, we add 3 to get log base 3 of x equals 3. And now we're back to where we started at the beginning of this video. change the log to an exponent. 3 squared equals x, or x equals 9. 3 cubed equals x, or 27 is equal to x. Checking the original, both of these keep it positive because it's just the log of x. Both these solutions are going to work for this problem. Sometimes quadratic in form can become very interesting to us when we start looking at trying to get the same base. Let's start with this problem first. Let's do 10 log base 4 of x minus 3 log base 8 of x equals 4. Both of these have different bases, so we're not going to be able to combine them and work with them unless we were to change these to have a common base. With 8 and 4, if we were talking about exponents, 8 and 4 would have a common base of 2. 4 is 2 squared, and 8 is 2 to the 4th, or 2 to the 3rd. So we are going to use the change of base formula. Remember, the log base a of b is equal to the log base, our convenient number, base c, of the inside divided by the log base c of the old base. Here, our 4 and our 8 would probably be best served with a base 2. So we have 10 log base 2 of x divided by log base 2 of 4. Minus 3 log base 2 of x over log base 2 of 8 equal to 4 still. Now that 4 and 8, let's rewrite them with exponents. 4 is really 2 squared, and 8 is really 2 cubed, because that's going to allow us to simplify using our property that the log base a of a to the x, if the bases match, the solution is the exponent. So now we have 10 log base 2 of x divided by, bases are the same, so the answer is the exponent, 2. Minus 3 log base 2 of x divided by, the bases are the same, so the answer is the exponent, equals 4. Well, this just keeps getting nicer because now those 3's divide out, and 10 over 2 reduces to 5. So we really have 5 log base 2 of x minus a log base 2 of x equals 4. We can do this a couple ways. We can make this x to the 5th and then change it to a division problem. Or we can say 5 minus 1 log is 4 log base 2 of x's, which is equal to 4. And then I'm going to divide both sides by 4, which gives me the log base 2 of x is equal to 1. Now all that's left is to convert this to an exponent. 2 to the first power equals x, or simply 2 equals x. We've got our solution. And what made this problem work was we identified a convenient common base so that we could start working with the logs together as a group. So if we've got different bases, we're going to have to do some work to get the same base. This first example, we looked at the base 4 and the base 2 and said, hey, the common base is a base 2. Sometimes it's not as obvious what the common base is. Sometimes we're working with a problem like log base 2 of x plus log base x of 16 equals 4. Here we've got a base of 2 and a base of x, and we really have no idea what the common base is for both of them. My recommendation in this case would be let's go with the number, not the variable. Let's do a log base 2. So we're happy with the log base 2, the first one. The second one, though, the log base x, is going to need some work. So we've got log base 2 of x plus, changing it to a log base 2, we keep the 16, we just have to divide by log base 2 of the old base, is equal to 4. Now here I don't like that fraction. So let's get rid of the fraction by multiplying each term by log base 2 of x. And when we do, the fraction divides out, and we have log base 2 of x times log base 2 of x. Well, that's log base 2 of x squared times itself. Plus log base 2 of 16. Well, gee, let's actually play with 16. Let's factor it. 16 is 2 to the 4th power, which means this is going to simplify to 4 in a minute. That's going to be nice. Equals 4 log base 2 of x. And what you notice we have again is we've got that log base 2 of x, one time it's squared, one time it's not. We're quadratic in form. Let's make it equal to 0 by subtracting 4 log base 2 of x from both sides. Log base 2 of x squared minus 4 log base 2 of x plus, remember if the bases match, the answer is just the exponent, equals 0. And now we're ready to factor this expression. Log base 2 of x squared is log base 2 of x times log base 2 of x. 4 is 2 times 2, and they're both negative. So that means they're both actually the same factors, so we're just going to do this once instead of twice. Log base 2 of x, add 2 to both sides, equals 2. Change it to an exponent, and 2 squared equals x. So that means x is equal to 4. Double check that doesn't make any negative logs, so we have our solution, x equals 4. This last part is really just variations on a theme, though. Our basic strategy for solving these logs is always going to be the same. If we have logs on one side, we'll write them as a single log and convert them to an exponent. If we have logs on both sides, we'll write them as single logs on each side. And since the bases are equal, the insides are equal. The variations that we looked at said, hey, if it's quadratic in form, we can factor it. If we have different bases, we need to get a common base or a convenient base, and then we can solve from there. Take a look at the homework, and we will see you in class.